weights, which are essentially just ordinary probabilities. So the density operator comes in two forms, in which you have either a set of probabilities, a set of states with corresponding probabilities, or a continuous range. In any case, the average value of an operator A measured across an ensemble is given by the trace of the density operator times the observable in question. And moreover, we distinguish a pure state as a special case of a density operator in which there's only a single term in the discrete sum here, which ends with 100% probability. In that case, rho is a projection operator onto the one-dimensional subspace spanned by the single pure state. If the state is not pure, that is to say, if it can't be written in this form and you have to write it as a sum of terms, then it's considered to be a mixed state. So we're conceiving of a pure state as a special case of a density operator, in effect taking the density operator as primary, and then pure states is something that's a special case of that, to be derived from that. This, in fact, is the most satisfactory point of view. However, the logical structure of what I've presented so far is not very satisfactory. It's in fact circular, because here I've defined the density operator in terms of pure states, and then I end up defining a pure state in terms of density operators. So I'll fix that up in a minute, but in the meantime, I just want to say that this conception of the density operator as a statistical weights of pure states is nevertheless useful. It's a useful way of thinking about the density operator, as in, for example, the Duncan experiment in which we had a beam which was polarized in a random direction. All right. So in any case, what I'd like to do is not to be too particular about the logical structure of this, but just to take these expressions from the density operator and derive certain properties of them. So allow me to do that. Unfortunately, I have to cover this up in order to use the board here. But I'm going to derive now some important properties of the density operator, which there's three that I want to mention. We call them A, B, and C. The first property of the density operator is that it's Hermitian. To expose the formula again, it's obvious that it's Hermitian because the probabilities are real numbers, and these outer products are Hermitian operators, the sum of Hermitian operators. The second property is that the trace of the density operator is equal to 1. This is easy to prove in a form of the discrete sum, because if I take the trace of rho, that's for simplicity, I'll deal with a case in which we've got a discrete set of probabilities and a discrete set of states. So the sum over the discrete probabilities, and then the trace of the outer product, which is the projection operator here, the trace of that is the inner product. That's how you take the trace of an outer product. And so it turns into the inner product of psi I with psi I. But we're assuming that the psi is normalized here, so this just turns into the sums of the probabilities, which is equal to 1 because probabilities have the 1. So the property of the density operator, that its trace is equal to 1, should be interpreted as being a normalization condition on the probabilities. Then the third property of the density operator, which I want to mention, is that rho is non-negative definite, which I'll write for short by just saying that rho is greater than or equal to 0. Because in the quotes, that's what it means, the same thing. I'll remind you that an operator is non-negative definite. It's the definition of non-negative definite if its expectation value with respect to an arbitrary state is non-negative. So let's take an arbitrary state phi, and let's sandwich it around rho like this, and ask what do we get. Well, again, using the discrete sums of the probabilities, this is the sum on I, probabilities fi, and we have phi scalar product with psi I times psi I scalar product with phi. And these last two factors here are complex conjugate of each other, so this is the absolute value of phi scalar product with psi I quantity squared. And you can see the entire sum. The probabilities are non-negative, these are non-negative, so the whole thing is non-negative, and we get the conclusion is a non-negative definite operator. This non-negative definite property is also connected with the interpretation of rho as describing probabilities of the system. The reason is that you may be aware of this, that this scalar product squared is interpreted in quantum mechanics as being the probability of finding the system if you measure the state phi, given that it was in state psi I initially, this thing squared is the probability of finding it in state phi. Never mind that. These types of interpretations come out of the postulates of quantum mechanics rather easily. But my point is that this has an interpretation as a probability And the FIs are probabilities, the probabilities of the psi i's. So altogether, what we're getting here is something that has to be a probability, and that's why it has to be a non-negative number. In any case, these are the three principal properties of the density operator. All right. Now, to go back to this point I was making earlier, that the density operator is primary, and pure states are to be considered a special case of them. An important part of this interpretation is the fact that the density operator is measurable. So, in a sense, we don't have to define it; we just have to say how one measures it. The idea is that if you compute the expectation values of enough operators or enough observables A, which are given by the trace of rho times A, one can determine rho from the results of the measurements. Now, I won't prove this in the general case, but what I will do is illustrate this for you for the case of the spin one-half system, which is actually an important basic practice. So, to go to the new board, the immediate project here is to show how you can measure the density operator in a spin one-half system. In a spin one-half system, the spin operator can be written as h bar over 2 times sigma. It is, of course, proportional to the magnetic moment operator, and if we were doing a Stern-Gerlach experiment, we really, from a physical standpoint, the Stern-Gerlach experiment measures magnetic moment. Since they're proportional, I'll just talk about spin. All right, so the idea is the following, is that if we measure the average value of the spin operator, that means we take our ensemble systems and we take the average value of Sx, Sy, and Sc and get three real numbers constituting a real vector here. One can measure that. The problem is, so given this, the problem is then how do we find the density operator from that? Spin one-half system has a Hilbert space which is two-dimensional, so the operators are represented by 2 by 2 matrices. And so the question is, how do we determine what the density operator is, what its matrix is? Well, to answer this question, I need to make a digression into some properties of 2 by 2 matrices and Pauli matrices. Let's let M be a 2 by 2 matrix, any 2 by 2 matrix. Then it's a fact that M can be represented as, which you may well know this fact, it's the fact that M can be represented as a linear combination of the identity matrix and the 3 Pauli matrices. And let's call the coefficient of the identity matrix A, and let's call the coefficient of the Pauli matrices B, which is a 3 vector, since there's 3 Pauli matrices. Altogether, there's 4 coefficients, which makes sense because a 2 by 2 matrix has 4 numbers in it. In fact, the identity and the 3 Pauli matrices form a basis of 2 by 2 matrices, in terms of which an arbitrary matrix can be expanded. To show that, you just need to show that these 4 matrices are linearly independent. I won't go through that, but it's straightforward to do that. But the question then is, how do we determine these expansion coefficients A and B? To answer that question, I want to make a little digression into some further properties of the Pauli matrices that I probably should have done in last week's homework, but I didn't. Anyway, here's what they are. These are trace properties of the Pauli matrices. Well, first let's talk about the trace of the identity. Trace of the identity is equal to 2, as is obvious because trace is the sum of the diagonal elements, and the identity matrix has got 1s to the diagonal. The trace of the individual Pauli matrices, all 3 of them, is equal to 0, as you can see just by looking at them. And then the third formula I want to quote is the trace of a product of 2 Pauli matrices, sigma I times sigma j, is equal to twice Kronecker delta ij. This third property actually follows from the last week's homework problem, where you show that sigma I sigma j is equal to Kronecker delta ij plus I times epsilon ijk sigma k. The notation used here is that delta ij is understood to be multiplied by the identity, so I'll put it in explicitly now. And if we take the traces of both sides, then on the left-hand side we get what we want here, and on the right-hand side, the trace of the identity is 2, so we get twice delta ij, and the trace of the sigma term, this term, is 0 because of this middle identity here, so that goes out and we take the trace. And so what you get is the result quoted here is that you get twice delta ij. So I'll really erase the proof of this and just leave the trace identities for Pauli matrices. By using those identities, we can solve for these coefficients A and B. Solve for the coefficient A, well, first of all, just take the trace of both sides of this equation. trace of m is equal to a times the trace of the identity, which is just twice a, plus the trace of that term, which is 0, because b is just a vector of numbers, and the trace of the sigma is 0. So it's 2a plus 0. And the result of this is that we find that a, the coefficient a, is 1/2 the trace of m. Likewise, if I take m and multiply by, let's say, sigma I get sigma I times one of the Pauli matrices. Sigma I times m is equal to a times sigma I plus sigma I times b dot sigma. I'll write this as bj sigma j using the summation notation on the j's. These are just numbers, so I can move them to the left. And what I have in terms of matrices is just the product of sigma I sigma j. Now, if we take the trace of both sides of this, we get trace sigma im is equal to 0 in the first term, and from the second term we get b sub j times twice delta ij using the trace expression up there, which is the same thing as twice b sub I, doing a little bit of three-dimensional tensor analysis. And this is equivalent to saying that the vector b is equal to 1/2 the trace of the Pauli matrices sigma, the vector matrices sigma multiplied times m. So these two boxes here are the main results for the expansion of a 2x2 matrix as a linear combination of identity and Pauli matrices. Here's how you get the coefficients. All right. Now to return to our problem, which is given the expectation value of spin, how do we find the density operator? Let's say, first of all, the density operator in the standard plus and minus S sub C basis is a 2x2 matrix. So it can be written as A times identity plus B times sigma. And the question is just what are the coefficients? Well, so I'm just interpreting, calling it rho now instead of m. So what you see right away is that A is equal to 1/2 the trace of rho. Well, the trace of rho is equal to 1. That's a normalization condition on the probability. So A is equal to 1/2. And as far as b vector is concerned, that's equal to 1/2 the trace of rho times the, it's trace of 1/2 rho times sigma, using, again, just replacing m by rho is all I'm doing. However, allow me to take this expression and to multiply and divide by h bar over 2, because h bar over 2 times sigma is the spin. And if I do this, this becomes 1/2 times 2 divided by h bar times the trace of rho s. But the trace of rho s is the average value of the spin, which is something you can determine experimentally. And so this turns into 1/2 times 2 over h bar times the expectation value of the spin vector. And the result of this is that if I take these a and b coefficients and plug them in here, then what we get is that rho is 1/2 of the identity plus 2 over h bar times the expectation value of spin dotted into sigma. And that's the answer to our problem. Namely, given the average value of spin, how do you determine the density operator? This is it. This is an example of how, of the general principle, that the density operator is measurable if you make the measurements of a sufficient number of observables. This is a simple case because there's only, just a second, because there's only a two-dimensional Hilbert space. And in higher dimensions, you have to obviously make measurements of a larger number of operators. But this illustrates the general principle. Yes, there's a question.
How do you know rho and sigma can be?
Because I don't. Rho is a 2x2 matrix, and sigma is a three other 2x2 matrices, and in general they don't commute.
So here we have B equals trace of sigma m, and there we have rho.
Oh, I see. You were concerned about the order of the... Yes. One of the properties of the trace is that you can cyclically permute the factors and the answer doesn't change. So it doesn't, I was probably sloppy about the order I wrote it, but in fact it doesn't matter. Okay. All right. So this is an example of this. Now, before leaving this example, let's ask a further question. Let's ask what are the conditions such that this density operator represents a pure state? Perhaps you'll recall that in the case of the thermal beam, we found that the density operator was just 1/2 the identity. That was because the expectation value of the spin was 0, remember? So you see this formula agrees with our earlier result in that. But let's ask the question, what's the condition that this should represent a pure state? Well, I'll remind you, a pure state is when the density operator can be written in terms of a some normalized cat style like this. It's a projection operator onto a one-dimensional space, which is spanned by the cat in question. And since it's a projection operator, it means that its eigenvalues are either 0 or 1, or the eigenvalues of rho. Now, this is not generally true. It's only true when rho is a projection operator. So this is for a pure state. For a pure state, the eigenvalues of rho are either 0 or 1. And moreover, the eigenvalue 1 must be non-degenerate. That's to say, the eigenspace must be one-dimensional, because then the psi, the state vector for the system, is a vector that spans that one-dimensional subspace. So this is a criterion for a pureness of a density operator. It has to have only these two eigenvalues, and the one eigenvalue must be non-degenerate. Well, what about this density operator? Under what conditions does this represent a pure state? Well, leave it as an exercise for you that if you take this expression for an arbitrary 2x2 matrix, and let's let A and B be real, because if they're real, this implies that the rho is Hermitian, and rho is Hermitian, so these are real vectors now. I'll leave it as an exercise for you to show that the eigenvalues lambda are equal to A plus or minus the absolute value of vector B. It's just a straightforward exercise in a 2x2 matrix. But in our particular example, where rho has this form and the A and B coefficients are given by these expressions here and here, we can plug this in and ask what are the conditions if one of the eigenvalues should be 1 and the other one 0. Well, this is going to require that A, let's say, plus the absolute value of vector B is equal to 1, and A minus the absolute value of vector B is equal to 0. These two conditions imply that A is equal to the magnitude of B, which is equal to 1/2. Well, we already knew that A was equal to 1/2 because that was necessary to get the trace condition on rho. But now we find that in order to get the two eigenvalues of 0 and 1, the magnitude of B must be also equal to 1/2. So the B vector here is this thing here. It's 2 over h bar times the expectation value of S. So what we conclude is that rho is pure, a pure state, if and only if the expectation value of S is equal to h bar over 2 times the unit vector. Let's call it n hat. Some unit vector. And in fact, one can show that generally the magnitude of S is less than or equal to h bar over 2. This is the maximum value of the magnitude of the expectation value of the spin can take on. In that case, then we can write rho in this form as equal to 1/2 identity plus the unit vector in question dotted into the Pauli matrices. And for a spin 1/2 system, this is the general form of the density operator for a pure state. Now, I'll leave it as an exercise for you to figure out what psi is equal to. This is, of course, going to be the eigenvector of this matrix with eigenvalue plus 1, and so it's straightforward to figure it out. But this then gives you the wave function. This is how you get a wave function starting from a density operator. Notice that if you don't have a pure state, then there is no wave function. Okay. Now, so that's all I'm going to say about the measurement of the density. It's an important basic practice, as a matter of fact. Now, what I'd like to turn to now is quantum statistical mechanics. Statistical mechanics is applied whenever you have incomplete knowledge about the state of the system. In classical mechanics, it means you only have some probability distribution. Probabilistic sense is you only know the state of the system, the classical state, in a probabilistic sense. It's usually described by a probability distribution in the classical phase space, which is called the Liouville distribution. In quantum mechanics, the repository of all the information, the probabilistic information you have about the system, is actually the density operator. So the density operator is a central object in quantum statistical mechanics. Now, different density operators are appropriate in different circumstances, depending on what knowledge you happen to have. And just as in classical mechanics, there are different ensembles one might consider. So one can think of different density operators corresponding to different ensembles, different physical situations where one has more or less knowledge about a system. Now, as you know, one's knowledge about a system is quantified by the entropy. To give you a little history of the entropy was originally conceived in the 1850s and 1860s by Kelvin and Clausius. It was originally conceived of as a quantity that applied to a system in thermal equilibrium, like a bottle of water at a given temperature. And it's still considered this is one of the ways entropy is used. However, somewhat later, Boltzmann realized that the concept of entropy could be generalized also to non-equilibrium situations, and that the entropy became, in effect, a functional of the probability distribution of the system. And Boltzmann wrote down this famous formula for what that probability is, or what that definition of entropy is. So to make a long story short, if I take Boltzmann's formula, which was classical from the 1870s or 80s, I'm not sure the exact date, and make the obvious transcription into quantum mechanics, and what you get is an expression for the entropy. It now becomes a functional of the density operator. And this is the formula. The entropy is minus k, which is the Boltzmann constant, times the trace of rho times the logarithm of rho, where rho is the density operator. And this can also be written as minus k times the expectation value of the logarithm of rho, because remember the trace of rho times an operator is the average value of it. It's the average value of log rho is seen across an ensemble. I'm not going to justify this. That's another course to do it, but this is the definition of entropy in quantum mechanics. Now, I will remark, however, that what we see here is a logarithm of an operator. Remember, rho is an operator. It's a Hermitian operator. It's an observable. Back when we were doing the notes number 1 on the mathematics of quantum mechanics, I think I mentioned this when we were in a lecture about the function of what it means to talk about the function of an observable. The idea is that you go to the eigenspaces of a given observable and to compute a function of the observable. The function of the observable has the same eigenspaces and therefore the same projectors, but the eigenvalues get replaced by the function of the eigenvalues. That's how you make a function of an operator. If the function is a polynomial or something that can be expanded in a Taylor series, you can also conceive of the function of an operator by means of the polynomial or the series of the operator. In that case, the two definitions are the same. The logarithm doesn't have any Taylor series expansion, not about rho equals 0 anyway. Anyway, the concept of a function of an operator is defined for all observables, even for rather strange functions. In this case, it's just the logarithm, which is not the strangest that we'll ever see. All right. Now, so as I say, this is a functional of the density operators. So different density operators give you different entropies. One remark is that if you have a pure state, the entropy is 0. And if you have a mixed state, the entropy is always positive. So a state of minimum entropy is where you're actually in a pure state. Now, the game we frequently play here is we impose constraints on the system. We say, for example, we know quantity I'll call E, which is defined as the average value of the energy, the Hamiltonian, which more exactly is the trace of rho times h. And let's suppose this is given. So in other words, let's suppose we have an ensemble in which the average energy is known. There's also, of course, a normalization of rho, which is equal to 1. This is also a given. It's another constraint of rho. And if we maximize, this is really Boltzmann's game that we're playing here. If we maximize the entropy subject to the constraints that the average value of energy and the normalization are given, then it's possible to determine what S is. And S turns out, excuse me, not what S is, what rho is. And it turns out that rho, in this case, becomes proportional to e to the minus beta h, where h is the Hamiltonian. The beta here is a Lagrange multiplier in the constrained maximization process, but it's otherwise 1 over kt, the usual beta parameter in statistical mechanics. So this is easy to do, but I'm not going to do it because it's the wrong course. But I do want to point out that you get this density operator under these conditions, which stands for the canonical ensemble. That is to say, it's an ensemble that physically means a system is in contact with a heat path, or you create your ensemble of systems by taking and putting them in contact with the heat path, removing them and doing an experiment on them, such as measuring their energy or some other observable. All right. The normalization constant that appears here, this is just proportionality, but the normalization constant is is traditionally called 1 over capital Z, so we write rho as equal to that thing with 1 over capital Z. And the normalization is determined by demanding that the trace of rho is equal to 1. And if you do this, then this implies that Z, which is a function of the thermodynamic parameter beta, is the trace of e to the minus beta h. And the Hamiltonian, let me put a box around that because that's a basic result in quantum statistical mechanics. Z beta, of course, is the partition function. Stands for German Zustandssumme, sum of states. The trace is, of course, the sum of the diagonal elements of an operator. Here we've got an exponential operator of the Hamiltonian. A convenient basis in which to do the sum of diagonal elements is the energy eigenbasis. So let's introduce an energy eigenbasis. Let's write it this way as nr is the basis. Let's say the energy eigenvalues are En. And this is the same cat all over again. Let's say these are normalized here. So that n labels the energy eigenvalue, and the r is an extra index used to resolve degeneracies, in case there are some. So let's say r goes from 1 up to, let's call it g sub n, which is the number of degenerate energy eigenstates. Then, this trace, I'll remove this box, this trace can be written this way. It's a sum on n and r of diagonal elements, let's say nr, sandwiched around e to the minus beta h and r, like this. However, since these are energy eigenstates and we're acting on them by a function of the Hamiltonian, it just brings out a function of the eigenvalue. So this gets replaced by e to the minus beta e sub n, the energy eigenvalue of this state. And the result is this turns into a sum on n and r of e to the minus beta e n times the scalar product of nr with itself, which is 1 since the states are normalized. So we can write this as a sum on nr of e to the minus beta e n. Or since the sum n does not depend on r, the degeneracy index, we can write this as just the sum on n times the order of the degeneracy times e to the minus beta e n. And I end up after this with the formula that you probably learned in undergraduate stat mech courses for the partition function that's given by this in terms of degeneracies and energy eigenvalues. It's really a normalization of density out there. Now, there's a little secret that they never tell you in undergrad stat mech courses. You spend a lot of time calculating the partition function because it's useful for finding things like the equation of state, and a lot of important things can be derived from it. But it actually does not give you complete information about the statistics of the system. If you want that, you really need a density operator and not just a trace of this thing. You need the whole thing. So, for example, if you're talking about a gas, maybe it's not an ideal gas, and you want to know correlations between particles, that's something you can't get from the partition function. You need the full density operator. All right. Now, I think that was the main thing I wanted to say about that, except I'd like to now give you an example. This is an example of the density operator so you can see how it works in practice. Roughly speaking, the basic idea is that the different energy eigenstates in thermal equilibrium have probabilities that are proportional to just the Boltzmann factor. So that's an easy rule, e to the minus beta times energy. It's an easy rule. These are not normalized probabilities, but if you're only interested in relative probability, it's easy to do. Let me give you a physical example of that. I want to talk about a hydrogen gas, but I mean atomic hydrogen and not the hydrogen molecule. Ordinary hydrogen gas in the laboratory is H2, and I don't want to talk about that. Gas of atomic hydrogen occurs in astrophysics. So galaxies are full of large clouds. Many of the clouds contain atomic hydrogen predominantly, not molecular hydrogen. It's a simpler system, actually. Atomic hydrogen, of course, has an electron and a proton, and they both have spins. Those spin one-half particles, so either spin can be up or down. There's a total of four spin states. Because of magnetic interactions between the electron and the proton, these states are actually split into two energy eigenstates called the singlet and the triplet state. And so let me tell you about them a little bit. There's a singlet and triplet state. Schematically, the singlet looks like this, where the spins are opposite, and the triplet states where they're parallel. And if I write these states as Sm, where S is a total spin and M is a total magnetic quantum number, and the singlet state is 0, 0, and the triplet state is 1, n, where m is equal to 0 and plus or minus 1. That's why it's called a triplet state, because there's 3 states. Let's call the singlet state also 0 and the triplet state 1, or we may call it E0 and E1, because they actually have different energies. In fact, the E0 is really the ground state of the hydrogen atom, and E1 is slightly above it. They're split in energy by this magnetic interaction that I mentioned. The energy difference between these two states, this is called hyperfine splitting. The energy difference between these two states, if it's translated into a wavelength unit for the photons that are emitted on the transition, is 21 centimeters. So this is the famous 21 centimeter line. It's important in astrophysics. If you translate that into temperature units, it's about 5 kelvins. The actual temperature of these gas clouds out there is comparable to 5 Kelvin, or in fact maybe somewhat larger than that. But in any case, the point is that the temperatures are such a magnitude that the Boltzmann factor is important in determining the relative populations of these two energy levels in these clouds of atomic hydrogen. And in particular, the relative probabilities of the two levels are e to the minus beta E0 and e to the minus beta E1. Except it's a little bit tricky because E1 has got a 3-fold degeneracy, so I need to multiply by 3. Those are the relative probabilities. And to put it another way, the partition function Z of beta is just equal to the sum of these two terms like this. It's the sum of the Boltzmann factors times the degeneracies. What is the density operator? Well, it's 1 over Z, that's the normalization. In the singlet state, it's e to the minus beta E0. And then there's a projection operator on the singlet state like this. And then for the triplet state, it's e to the minus beta E1. And then what you've got is a sum over these magnetic quantum numbers of 1m, outer product of 1m. This sum is the projection operator onto the degenerate triplet state. And this outer product here is the projection operator onto the non-degenerate ground state. And here is a density operator describing those atoms out in the galaxy. Now, there's a question so the probabilities can be just read off as the coefficients of these terms, the various terms here. You see that the 3 excited states all have the same probability, they have the same energy, and therefore the same probability. Now, what we've got here is 2 states with certain probabilities. If I took a linear combination of the ground state and some of these first excited states, then from the coefficients of the linear combination, I would also have certain probabilities. The question arises is, what's the difference between this density operator and some linear, if there is one, and some linear combination of the ground state and the excited state? The answer is there is a difference. This is what you call an incoherent mixture. It's the same thing as saying that it's a mixed state. Whereas a particular linear combination of the ground state and the excited states would be what you call a coherent mixture, which would be a pure state. Let me try to describe this in a more general language without reference to this hyperfine transitions in hydrogen. Let's say that we have a density operator for some system now. Let me just make it any old system. And for simplicity, let's suppose the energy eigenstates are non-degenerate, so I'll write this thing in like this with weights at n. This is really the same notation I was using earlier for a general density operator. The Fn's are the weights, and they're also probabilities, so they sum up to 1. This is the density operator. Let's also consider a pure state psi, which is given by its expansion in terms of energy eigenstates with some complex coefficients that look like this. This is what you're used to doing with expanding states. Now, if we have this linear combination of states, then you know the probability of finding a system in an energy eigenstate n is the square of the coefficient Cn squared. And these things are positive number, non-negative numbers that add up to 1, so they're just like these probabilities F here. The question is, what's the difference? Is there some physical difference between these two? Supposing the Cn squareds were equal to the F's, is there any difference between these two? The answer is that if you're only going to measure energy, you couldn't tell the difference between the two because you get the same probabilities for the energies. But if you want to measure other observables, then there is a difference. There's a physical difference between them. This is a mixed state. This is a pure state. To understand this, allow me to do the following. First of all, let me take this complex number Cn, and let's take its absolute value and call it just An like this. And then let's write Cn is equal to An, which is its magnitude times the phase factor, really like phi. And let's just write C in terms of amplitude and phase form. Then let's take this pure state psi, and let's compute the density operator that corresponds to it. That's, of course, just the outer product of psi with itself. We're taking this series, forming its complex conjugate, to form the graph here, and multiplying them together. You get a double sum that looks like this. It's a sum on n and m, with a sub n times a sub m times e to the I phi n minus phi m times the outer product of n with m. It's represented as a matrix in the energy representation. But as you see, it's not diagonal. This matrix is diagonal. This one has off-diagonal elements. And so that's one of the differences between this density operator and this one, which is a pure state. Now, in many circumstances, the phases which appear here are not known as well as the amplitudes. The amplitudes are related to the probabilities. The phases in many circumstances are not as well known. One of the reasons is that the phases are time-dependent. In fact, by the Schrödinger equation, phi n is equal to minus En times t, where En is the energy eigenvalue. So these things evolve in time. The phases keep increasing in time. If you're taking an off-diagonal term where n is not equal to m, then the energies are not equal, and so the difference between these phases grows in time. And ultimately, it'll get to be an arbitrarily large multiple of 2 pi. If there were some errors in the energy eigenvalues, or you didn't know them precisely, then those errors would ultimately result in phases that were phase differences, even that were completely unknown to within a multiple, to within a factor of 2 pi. In other words, they become effectively random phases after a sufficiently long time. So what this suggests is that we go from this pure state into a statistical mixture in which the statistics is given by a random phase ensemble. And these phases are all independent, statistically independent of one another, and uniformly distributed between 0 and 2 pi. If we do that, then we'd like to replace this pure density operator by a statistical average over phases. Well, the average over phases only affects this term because nothing else depends on phases. So let's take e to the I phi n minus phi m, and let's average it over the phases. And what do we get? Well, if n is equal to m, these two phases are equal, and so they cancel out and take the average value of 1, and the answer is 1. But if these energy levels are not the same, then you've got independent random variables that are uniformly distributed around a circle, and the average is 0. So this average turns into a chronicle delta nm. And so if we take the statistical average of this pure state, what do we get on the right-hand side? This thing is going to average to chronicle delta nm. It collapses into a single sum. It becomes the sum on n of an squared times the outer product of n with n. In other words, it looks just like the Boltzmann. It looks just like the Boltzmann, or this is the Boltzmann ensemble if the FNs are the Boltzmann factors. More generally, this is an ensemble that's diagonal in energy representation. And that's what we get in this random phase ensemble. So in particular, the ensembles that the canonical ensemble in thermal equilibrium can be thought of as an ensemble in which the probabilities of being in different energy eigenstates is known, but phases are completely unknown. So it's equivalent to this point of view. All right. Now, so that's enough about the canonical ensemble. In fact, that's all I want to say about the density operator. What I'd like to do now is to go back to the postulates of quantum mechanics. This is all in the notes, so you don't have to copy this down. Go back to the postulates of quantum mechanics, which I presented earlier in an incomplete form, because it was incomplete because we were using pure states, which at that point was undefined, and revise those postulates now in terms of density operators. So some of the postulates are the same as before. One is still the same. The physical system corresponds to a Ket space. 2 is different. The state now, the system, corresponds to a density operator rho, which is a Hermitian operator with unit trace and whose is non-negative definite. That's what that expression means. 3 is still the same as before. Every measurement process corresponds to an observable and a complete emission operator with X on the Ket space. Item number 4 is the same also. The results of the measurement are the eigenvalues of the observable, either the discrete or the continuous, depending on what you have. 5 is a probability postulate. It now becomes modified. The probability finding the result A equals AN in the discrete case is a trace of rho times Pn, where Pn is a projector onto the corresponding eigenspace of the operator A, with eigenvalue A sub n. In the continuous case, the probability finding A in some interval, let's say from A0 to A1, is a trace of rho times the projection operator that corresponds to that interval, which is the integral of the outer products along the interval in the continuous variable A. Here I've included the sum over the degeneracy index in case there's degeneracies. And here's the interval is I. So this is the revision of the first 5 postulates. And as far as the 6th postulate goes, then I'll remind you that in the case of the pure states that we talked about a couple of lectures ago, the collapse postulate said that after the measurement, the system's been projected onto the eigenspace of the observable whose eigenvalue you got in the measurement, so-called collapse postulate. That is replaced by something else when you have density operators. And I'm leaving that as an exercise for you to fill in item number 6 here. It's a good exercise for thinking about what density operators mean. All right, so that's all for density operators. And now I'd like to turn to a new subject. Are there any questions about density operators before I go on? Yes?
Is there a more general criterion for looking, like, is there like a to tell what the state is here?
Yeah, there are several criteria, and I mentioned some of them in the notes. So here in the lecture, I only mentioned the more obvious one where you diagonalize and get the eigenvalues. That seldom always works. There's easier ones, though. It turns out that rho squared equals rho if and only if it's pure. You can see that if rho is psi, if you square it, what you get is rho squared is, you see, and this is just 1. So rho squared equals rho in a pure state. But the converse works too. It's pure if and only if this condition holds. Another condition is the trace of rho squared. Actually, the trace of rho squared is always less than or equal to 1. But if the trace of rho squared is equal to 1, then it's pure. And yet another one is the entropy. The entropy is equal to 0 if and only if it's pure. This is maybe not so easy to use because to compute the entropy you need to get the log of rho, and so you need to get its eigenvalues and eigenvectors. And if you're going to do that, you might as well use a simpler criterion. But still, it's interesting because zero entropy means that you have the maximum information you can have about the system. It's not a pure state. That doesn't mean that you've eliminated statistical uncertainties in the measurement process, because quantum mechanics is intrinsically statistical. So there will still be statistical distributions and answers for then the different systems. But this is the maximum we can get. Are there any other questions? All right. So what I'd like to do now is to turn to the question of spatial degrees of freedom. We mostly talk about spin. So let's talk about spatial degrees of freedom now. To make this simple, let's first of all take a 1D case so that we're thinking of a particle moving on a line here, coordinate x. And let's also suppose that there's no spin or any other variables around except the position variable. That's not quite what I mean. There are other variables around like momentum and so on. But what I do mean is that a complete set of commuting observables, which is what you need to measure in order to get things down to one-dimensional subspaces in Hilbert space, consists of just the x operator itself. That's all there is. I'm going to use the notation putting a hat over the x to indicate an operator. I'm sorry because sometimes I use the hat to indicate a unit vector, but it's hard to get a good notation for this. So in the present case, this means operator. And this is to be contrasted with x without the hat, which stands for a number. There's something I should have told you a couple of lectures ago, so I'll tell you now. It's a little bit of a digression. There's an old terminology due to Dirac, which is that he talks about what he calls Q numbers and SU numbers. And you hear it, it's useful terminology, so I'll tell you what it means. A Q number basically means an operator. And a C number means an ordinary number. So we usually use this terminology when we want to draw the distinction between, let's say, an operator and its eigenvalue. So in any case, the x hat here is the q number, and the x, which is the variable, the coordinate, is the c number. Now, so we'll just take it as given that x hat by itself in this one-dimensional problem is a complete set of commuting observables. When we measure x, measure position, of course, we get a continuous set of values. So if I take the eigencat eigenvalue problem for the operator x hat, it looks like this. I label the eigencat by its eigenvalue, and multiplying operating with x hat just brings out the eigenvalue. This must be a member of the continuous spectrum because we know measuring position takes on continuous values, at least until we get down to the Planck scale where nobody knows what happens. And as a result, the normalization of these position eigencats must be understood in a delta function sense, like this. And moreover, the resolution of identity is an integral from minus infinity to plus infinity, the outer product of x with x. This all just follows from basic formulas in the quantum mechanics. Now, let's inquire as to the probability of measuring x to lie in some interval. And let's say this is with respect to a pure state. Having done the density operators now, you're going to find that in most of the rest of the course we'll be talking about pure states. This is, as I've said, and I think in lecture and certainly in the notes, this is a bias of quantum courses, but in real experiments you're always using density operators and not wave functions, not nearly as much. Anyway, let's say we have a pure state psi, and we're interested in the probability of measuring x to lie in a certain interval. Well, by the postulates of quantum mechanics, this is psi sandwiched around a projection operator that corresponds to that interval, where that projection operator pi is the interval here, is the interval x0 to x1, is the interval from x0 to x1 of dx of the outer product of x with x. It looks just like the resolution of the identity, except the interval doesn't go all the way to infinity, just over the interval. In any case, this means that this probability is then equal to the integral dx from x0 to x1 of psi scalar product of x times x scalar product of psi. Now at this point, we make a definition. We define the quantity x scalar product of psi to be equal to the wave function psi of x. And in this manner, we sort of derive wave functions from the Ket formalism, which was promised earlier. And with that definition of the wave function, you can see that this interval, the first factor is the wave function complex conjugate, the second factor is the wave function. So this is an interval x0 to x, x1, of dx, the absolute value of the wave function squared. And so the result of this is that the probability of lying in this interval is the interval of psi of x squared. Therefore, psi of x squared is the probability density, which of course you know that this is how it comes out. Now, this definition here, let's see. Yes, this definition here can be thought of in another manner as well. This is in effect a part of a translation table that takes you from Ket language to wave function language. If you're given the Ket psi, you want to find the wave function psi of x, you just take the scalar product from the left with the position eigenvalue. How do you go the other way? Suppose I'm given the wave function and I want to find the Ket psi. Well, the answer to that is I take the projection operator here and multiply both sides by the Ket psi. So I get the Ket psi itself on the left-hand side. On the right-hand side, I get the scalar product of x with psi, but by our definition, that's the wave function. And so the result is we get this formula. This Ket psi is equal to the integral, this is all from minus infinity to plus infinity, of dx of Ket x times psi of x. And this goes the other way. If you're given psi of x, you can now find the Ket. But it does something else too. It shows you that the wave function is nothing but the expansion coefficients of the quantum state, the vector in the Hilbert space, with respect to position basis. This is one of the reasons why we should think of psi of x as, in some sense, not having a terribly privileged role, because you can take a vector psi, you can expand it with lots of different bases. It's an arbitrary choice of bases. And this is just one of them. It's just a position basis. All right. Now, there's another point to be made here about this, which is that the wave function psi of x is single valued. It's single valued because it's nothing but the expansion coefficient of the state vector psi with respect to the position eigenpaths. So for a given value of x, naturally it has only one value. This is an issue which arises sometimes in solving the Schrodinger equation, which is, of course, what you do in introductory courses. And when you separate the variables and so on, there's at some point we have to say, well, we have to require the wave function to be single valued, and what's the physical justification for that? Well, this is really it. This is the reason the wave function is single valued. Right. Now, I've done this all in one dimension, but it's easy to generalize this to 3 dimensions. If we do it in 3 dimensions, then there are really 3 position coordinates, x, y, and z. And so each one of them corresponds to an operator. It's a measurement of the 3 coordinates like this. And now the complete set of commuting observables, still ignoring spin, assuming there's no spin, complete set of commuting observables is the 3 variables x, y, and z. Or I'll also write this as x hat I, where I equals 1, 2, and 3 with an index 1. Now, one thing to say right away about these 3 observables is that they commute with one another. X hat I, commutator of x hat j is equal to 0. How do I know that? I remind you that the commutativity of operators is something that can be subjected to experimental tests. It has to do with the fact that if operators commute, then you can measure them in either order, and you get the same statistics on the doubly filtered system. So in this case, if we measure x, for example, by putting a slit in the y direction, so that you're slit in, you want this, you want to measure x, you put the slit in the y direction, just like this. And if you want to measure y, you put the slit in the x direction. And so what it leaves behind is a little square. And let's just say, one can say that experimentally it can be determined that the statistics of the ensemble you get doesn't matter when you put the x slit first or the y slit first. It's the same answer. So this is equivalent to the commutativity of these operators. By the way, they have to commute if they're going to form a complete set of commuting observables, because that's what that C stands for, is commuting. All right. Well, in this case, we have eigencats. We have simultaneous eigencats of the 3 observables. We can call that x vector like this. And these are actually simultaneous eigenvalues of the 3 operators. X hat I equivalent x vector is equal to xi, the eigenvalue times x vector. This is actually 3 simultaneous eigenvalue equations. Most of the formalism that I just described in the one-dimensional case goes over with kind of only obvious modifications, going over to the 3-dimensional case. And so I won't bother to write all that out. It should have resolution of the identity now becomes the 3-fold interval for all space. Here, instead of talking about the probability of the interval, one talks about the probability of finding the particle in a region in space. The absolute value of psi squared is the probability density in 3-dimensional space, and so on. It's a straightforward generalization of 3 dimensions. Okay, so I'll stop now. Just tell you next time, which is coming up tomorrow morning, I'll be telling you about translation operators. I have now some important properties of the density operator, which there's 3 that I want to mention. We call them A, B, and C. The first property of the density operator is that it's Hermitian. To expose the formula again, it's obvious that it's Hermitian because the probabilities are real numbers, and these outer products are Hermitian operators, the sum of Hermitian operators. The second property is that the trace of the density operator is equal to 1. This is easy to prove in a form of the discrete sum, because if I take a trace of rho, that's for simplicity, I'll deal with the case in which we've got a discrete set of probabilities and a discrete set of states. The sum over the discrete probabilities, and then the trace of the outer product, which is the projection operator here, the trace of that is the inner product. That's how you take the trace of an outer product. And so it turns into the inner product of psi I with psi I. but we're assuming that the size normalized here, so this just turns into the sums of the probabilities, which is equal to 1 because probability is exactly 1. So the property of the density operator that's trace is equal to 1 should be interpreted as being a normalization condition on the probabilities. Then the third property of the density operator, which I want to mention, is that rho is non-negative definite, which I'll write for short by just saying that rho is greater than or equal to 0. Just put this in the quotes, that's what it means, the same thing. I'll remind you that an operator is non-negative definite. Its definition of non-negative definite, if its expectation value with respect to an arbitrary state is non-negative. So let's take an arbitrary state phi, and let's sandwich it around rho like this, and they ask what do we get? Well, again, using the discrete sums of probabilities, this is the sum on I, probabilities fi, and we have phi scalar weights, which are essentially just ordinary probabilities. So the density operator comes in two forms, in which you have either a set of probabilities, a set of states with corresponding probabilities or a continuous range. In any case, the average value of an operator A measured across an ensemble is given by the trace of the density operator times the observable in question. And moreover, we distinguish a pure state as a special case of a density operator in which there's only only a single term in the discrete sum here, which enters with 100% probability. In that case, rho is a projection operator onto the one-dimensional subspace spanned by the single pure state. If the state is not pure, that is to say, if it can't be written in this form and you have to write it as a sum of terms, then it's considered to be a mixed state. So we're conceiving of a pure state as a special case of a density operator, and in fact taking the density operator as primary, and then pure states is something that's a special case of that, to be derived from that. This, in fact, is the most satisfactory point of view. However, the logical structure of what I've presented so far is not very satisfactory. It's in fact circular, because here I've defined a density operator in terms of pure states, and then I end up defining a pure state in terms of density operators. So I'll fix that up in a minute, but in the meantime, I just want to say that this conception of a density operator as a statistical weights of pure states is nevertheless useful. It's a useful way of thinking about the density operator, as in, for example, the Duncan experiment in which we had a beam which was polarized in a random direction. All right. So in any case, what I'd like to do is not to be too particular about the logical structure of this, but just to take these expressions from the density operator and derive certain properties of them. So allow me to do that. Unfortunately, I have to cover this up in order to use the board here. But I'm going to derive psi I times psi I scalar product with phi. And these last two factors here are complex conjugates of each other, so this is the absolute value of phi scalar product with psi I quantity squared. And you can see the entire sum. The probabilities are non-negative, these are non-negative, so the whole thing is non-negative, and we get the conclusion is a non-negative definite operator. This non-negative definite property is also connected with the interpretation of rho as describing the probabilities of the system. The reason is that you may be aware of this, but this scalar product squared is interpreted in quantum mechanics as being the probability of finding the system that you measure the state phi, given that it was in state psi I initially, this thing squared is the probability of finding it in state phi. Never mind that. These types of interpretations come out of the postulates of quantum mechanics rather easily. But my point is that this has an interpretation as a probability, and the FIs are probabilities, the probabilities of the psi i's. So altogether, what we're getting here is something that has to be a probability, and that's why it has to be a non-negative number. In any case, these are the three principal properties of the density operator. All right. Now, to go back to this point I was making earlier, that the density operator is primary, and pure states are to be considered a special case of them. An important part of this interpretation is the fact that the density operator is measurable. So, in a sense, we don't have to define it; we just have to say how one measures it. The idea is that if you compute the expectation values of enough operators, or enough of this, which makes sense because a 2x2 matrix has 4 numbers in it, then in fact the identity and the three Pauli matrices form a basis of 2x2 matrices in terms of which an arbitrary matrix can be expanded. To show that, you just need to show that these four matrices are linearly independent. I won't go through that, but it's straightforward to do that. But the question then is, how do we determine these expansion coefficients A and B? To answer that question, I want to make a little digression into some further properties of the Pauli matrices that I probably should have done in last week's homework, but I didn't. Anyway, here's what they are. These are trace properties of the Pauli matrices. Well, first let's talk about the trace of the identity. Trace of the identity is equal to 2, as is obvious because trace is the sum of the diagonal elements, and the identity matrix has got 1 to the diagonal. The trace of the individual Pauli matrices, all three of them, is equal to 0, as you can see just by looking at them. And then the third formula I want to quote is the trace of a product of two Pauli matrices, sigma I times sigma j, is equal to twice Kronecker delta ij. This third property actually follows from the last week's homework problem, where you show that sigma I sigma j is equal to Kronecker delta ij plus I times epsilon ijk sigma k. The notation used here is that delta ij is understood to be multiplied by the identity, so I'll put it in explicitly now. And if we take the traces of both sides, then on the left-hand side we get what we want here, and on the right-hand side, the trace of the identity is 2, so we get twice delta ij, and the trace of the sigma term, this term, is 0 because of this middle identity here, so that goes out and we get the trace. And so what you get is the result quoted here is that you get twice delta ij. So I'm going to erase the proof of this. Variables A, which are given by the trace of rho times A, one can determine rho from the results of the measurements. Now, I won't prove this in the general case, but what I will do is illustrate this for you for the case of the spin one-half system, which is actually an important basic practice. So, to go to the new board, the immediate project here is to show how you can measure the density operator in a spin one-half system. In a spin one-half system, the spin operator can be written as h bar over 2 times sigma. It is, of course, proportional to the magnetic moment operator, and if we were doing a Stern-Gerlach experiment, we really, from a physical standpoint, the Stern-Gerlach experiment measures magnetic moment. Since they're proportional, I'll just talk about spin. All right, so the idea is the following, is that if we measure the average value of the spin operator, that means we take our ensemble systems and we take the average value of Sx, Sy, and Sc and get three real numbers constituting a real vector here. One can measure that. The problem is, so given this, the problem is then how do we find the density operator from that? Spin one-half system has a Hilbert space which is two-dimensional, so the operators are represented by 2 by 2 matrices. And so the question is, how do we determine what the density operator is, what its matrix is? Well, to answer this question, I need to make a digression into some properties of 2 by 2 matrices and Pauli matrices. Let's let M be a 2 by 2 matrix, any 2 by 2 matrix. Then it's a fact that M can be represented as, which you may well know this fact, it's the fact that M can be represented as a linear combination of the identity matrix and the 3 Pauli matrices. And let's call the coefficient of the identity matrix A, and let's call the coefficient of the Pauli matrices B, which is a 3 vector since there's 3 Pauli matrices. Altogether, there's 4 coefficients.